Let's start the BPS short talks. This is the first time we are hosting this kind of a format, and hopefully this will set the pattern for the next years also, perhaps. All right, so we'll start the session with Adrian Redder from Paderborn University. And Adrian will be talking about age of information in time-varying networks under strongly mixing communication. So Adrian, the floor is yours.
Yes, thank you. Thanks for the nice introduction and for the opportunity to speak about my work. I'm from Paderborn University, and I was introduced to the seminar from my supervisor, who's now in Karlstad, Arun Ramaswamy. He was a PhD student with Sarath Yasodharan, and so I'm mostly working in like distributed algorithms and learning, and especially the effect of communication networks on these kind of distributed algorithms. And one question that arose for us was how to formulate practically conditions for communication networks, especially with we're thinking about wireless networks, such that these algorithms can converge in the presence of potentially large age of information. So it's more like an engineering problem, and as I said, I'm electrical engineer by training and doing a Ph.D. in computer science and computer networks group. So it will be a little bit more elementary probably than the other talks, but I hope you're interested. So let's start with like the setting that I'm usually looking at. Usually I'm looking at like networks in the sense of either a fixed network or like a time-varying network. But for this talk, let's think about like a multi-hop network where information, an infinite stream of information, should travel from a source to a destination. And a simple model that we use in our work is that between each nodes we associate events that in some sense capture whether information or news information is passed from one node to another. So in this model, this is, for example, denoted by the event A12 at time step n, which says, okay, information goes, the news available information at node 1, which is the source, goes to node 2. And associated with these events, we can then consider the age of information, which we denote by delta sub 12, which then captures the freshness of the update at node 2 from node 1. So for example, here below, this process simply evolves by going back to age of information 1 if the associated event occurs, and it increases in the natural way if no event occurs at n. So for now, this is like a discrete event system, but you can also extend this naturally to the continuous case. So then what naturally follows is from these events on the like node to node level, you get that an age of information process associated with information flowing from source node 1 to source node D. And you can then naturally extend this to fully connected networks, for example, where each node is source and destination of information, which is then relevant for us in distributed optimization, where each node kind of generates data and has interest in the data of other agents. And then later come back to the application, and we hopefully see a bit about how they affect, for example, an optimization algorithm. Okay, so the questions that we were asking ourselves is especially what are some useful properties for the age of information, which we can use to analyze distributed optimization algorithms. And we are especially interested in some kind of growth properties, and to formulate them, we think that stochastic dominance is a really useful property. And what we define here is for this age of information random variables, we say that it has the stochastic dominance property with finite pth moment if then every realization of this age of information process is stochastically dominated by a single random variable. So it dominates for all n, that's the important point. And the finite pth moment says, okay, this dominating random variable should have its pth moments finite. So why is this useful as a property for age of information associated with networks? it's because you can naturally derive certain average expected age of information bounds. And for us, it was useful because we want to like get some useful bounds for the asymptotic growth. And what you can do with this stochastic dominance property, you get some kind of almost sure results for the asymptotic growth. And then maybe come to this a little later. So yeah, this is the kind of question that I'm now wanted to that I did address in my recent work, especially to find a representative and practically verifiable assumptions. And it should be like verifiable on a node-to-node level from an engineering perspective. And we might not have much information about like correlation between different edges. You can think about a real-world network where it's unsure whether success from node 1 to 2 has a high correlation with communication between other nodes. So this information might not be given. And as far as models are concerned in the distributed optimization literature, most people look at periodic communication or communication based on IID events, and these are not very representative for, let's say, wireless networks. So what we talk about today is when instead these communication or the success of communication, which we denote by this events A, is strongly mixing, which we define, I briefly recall next. And then especially how this stochastic dominance property translate from like single hops to multiple hops. So let's start with the first point. And for this, we need to recall some background on strong mixing, and I hope that you're a bit aware of this. So it's this measure of dependency, which is used for strong mixing, is like the one of the possible measures of dependency that you can define. And it's essentially like an upper bound to the like the difference to the case of like independence. And then for a stochastic process X, you define the information that is generated from time step L to M, and you define the subsigma algebra generated by this. And then you can define the mixing coefficients. This makes sense for a non-stationary process because we take the supremum over like all time steps, and we look here at displacement n. So this defines the mixing coefficient, and we then say that this process is strongly mixing if this goes to 0. If this mixing coefficient goes to 0 as n goes to infinity. So the assumption that we then made for a single hop are quite naturally. First, we in some sense need that with some positive probability an edge is present. And then this is formulated by assumption 1, and we are taking here union over certain events, so it doesn't need that at specific time instances success is possible, but it's fine if it's over a finite horizon. And the second point is now the strongly mixing assumption, and it's essentially that this indicator process associated with the events is strongly mixing. And we require some certain rate at which this now decays, and we will now relate this rate. We now use this rate to show that this stochastic dominance property is with the associated moments. And this moment will be determined by the rate at which this decays. So a quite natural theorem that you can then formulate is then that under these assumptions, you have this stochastic dominance property, this existence of a random variable for this single hop age of information with P determined by the rate at which it decays. And this is, you might naturally expect this, as you can maybe think about splitting the joint probabilities using the mixing coefficients. And this is exactly how the proof sketch looks like. I'm just going over it a bit quickly. So the essential idea is that you want to find a uniform upper bound independent of time n for the complementary CDF. And you can do this by like splitting up this interval from n minus m to n into certain intervals. And what you want is that the size of the intervals grows while at the same time the separation between those intervals grows. And with this, you can show like a preliminary upper bound to the CDF. And here you have this mixing coefficients. However, this is like not sufficient to immediately get the result. So in a second step, you need to improve this bound to get a geometric decay, which then follows from the first bound. And then you can get an improved upper bound, which then we can use in step 3 to show the theorem. And the main idea is then to use this upper bound for the complementary CDF to define this dominating random variable. And then you also need to choose this separation for the intervals a bit carefully. But then in the end, it's just a correlate from the formula of the expectation using the CDF. So now this has now shown our like stochastic dominance property for single hop networks. And then the natural question was, okay, how does age of information, stochastic dominance for age of information of single hops naturally translates to multi-hops? And this was like a kind of simple lemma that we formulated here. And here's now the figure again, where we have no single hops, and now we want to determine whether there's a dominating random variable for the multi-hops. And quite naturally, when you have a dominating random variable for each single hop, you get a dominating random variable for the multi-hop. And there's also a quite nice formula for the moments that you can show, and it is based on choosing certain coefficients to, in some sense, weight the expectation of each single hop. And you can show this inequality, which then naturally shows if each coefficients using constraint optimization with Lagrange multipliers. And this also shows that this bound gets sharp if, for example, let's say the mean of the age of information for one single hop is strictly larger than the others, then it will be dominate this, and it gets more and more sharp as one mean dominates all the others. So the main idea here is essentially to have have this following inequality, which essentially shows here for the case of 3 nodes that having a certain age of information in the for the first node, for the first edge, that is less than a fraction, and an associated fraction for the second hop, then you automatically get that this age of information associated with the multi-hop here is below a certain threshold. I just go over this quite quickly. You can just take in complements and evaluate this using the dominating random variables for the single hop, and then you just essentially define a dominating random variable as before and can evaluate the inequality. I think because of time, I just skip over this quite quickly. So essentially, you can now use this single hop or multi-hop formulation to get a correlate for, let's say, a strongly connected network. Yeah, since I'm already over 10 minutes, maybe we can go to the application in the discussion. It's essentially, I applied this to distributed stochastic approximation algorithms, where here in the example, we can look at equation at the iteration of x and x1 and x2. And here you see that in x1, it uses the variable of x2, but the aged version of it. So then using these properties with mixing, we can then show that this algorithm converges in the presence of a communication network that is strongly mixing. Okay, so what we have seen especially is that we can use strongly mixing node-to-node communication to get this stochastic dominance property with certain moment bounds depending on the mixing rate. And in a natural way, this property is transitive for multi-hop networks. So what I'm currently looking at, and I'm also open for ideas, is how to introduce spatial dependency in this setting, which especially for wireless networks is quite interesting. As you, for now, I've only looked at temporal dependency decay. And another interesting question is, of course, how for a specific process that is maybe unknown and only data is available, how can you estimate a strong mixing coefficient? And there's some recent work that I want to look at. because then when you can estimate the mixing coefficient, then there's the opportunity to, for example, have some online resource allocation to enhance the convergence of these algorithms, because you kind of know what you can expect for the moments of the age of information variables. Okay, that was basically it. Thank you for your attention. This is my recent preprint. I'm happy to hear your comments.
Thank you, Adrian. I'll allow everyone to maybe unmute themselves so that we can thank Adrian. And maybe just a minute.
Shrikar, maybe we can have applause at the end together. It will just save some time. Sorry, Adrian. Yeah.
Sure. Okay. So should we have maybe a minute of questioning or 2, 3?
Yeah, I think maybe a couple of questions.
All right. So is anybody wanting to ask any questions?
Let me ask one. So, Adrian, is your assumption A1 always true for IID sequences?
It is A2 or A1?
A1.
A1, I mean, if you like, the simplest model is like Bernoulli success, then it will always be satisfied, at least if the success is like has the associated bound. But of course, you can have a really degenerate process, which is IID, which maybe does not satisfy, which basically means no communication ever, right?
Okay. So it's not even in general, even for IID, it means, for independent random variables, A1 still needs to be checked.
Right, at least, right. A1 still needs to be checked. But of course, A2 is naturally satisfied for IID, and also for periodic communication. You can extend this a little bit. You may not have strong mixing of the process itself, but maybe the union process over some time interval, and then you naturally have strong mixing of periodic communication settings.
And stationarity is not assumed, right? You're not assuming stationarity.
No, stationarity is not assumed here.
Okay. Thanks.
You're welcome.
I guess we can move on to the next question, next talk. And there is a 15-minute break after the third talk. So if there are any questions, maybe we can accumulate them for that break. All right. Okay. So next is, thank you, Adrian. It was a wonderful talk. Next is Sayantan. Sayantan, could you please share your screen?
Yeah, I will. Is it visible?
Yes. Could you please make it full screen?
Yeah, okay.
All right. So, so next talk is by Sayantan Maitra, and he's from ISI Bangalore. He'll be talking about weak uniqueness for the stochastic heat equation driven by stable noise. Sayantan.
Okay, thank you very much. So hello everyone, and thanks for attending my talk. I want to talk about weak uniqueness of a stochastic heat equation that has a multiplicative stable noise with it. So I'll first introduce the model, and my model is this. I have a stochastic heat equation whose solutions I'm calling y on the real line, and I have attached to it a noise denoted by L, which is multiplicative in nature. So I'm multiplying the solution y to L. So what is L? L is a stable martingale measure in the sense of Walsh with index alpha, and it is a martingale measure. It's a noise of a very particular kind. It does not have any negative jumps. So formally, the noise is defined by this Laplace transform, which is equation 2. And okay, so equation 1 is pretty formal, and we want to understand it in a more rigorous sense. And more rigorously, we have this weak formulation of equation 1. So I'm not going to read it out, read all of it out, but I take phi, which is a smooth and non-negative rapidly decreasing function on the real line. and I okay, sorry. So yt comma psi is simply the L2 inner product of yt and psi. So I'm sometimes identifying yt with the measure which also has density yt. So I just want to point out that the first integral that you see here is a Lebesgue integration, while the second integral is a stochastic integral with respect to the martingale measure L alpha. All right, and I want to talk about the weak uniqueness or uniqueness in law of the solutions to this equation. So I have to introduce a few concepts. The first is weak existence. So weak existence of a solution to the equation. So I say the equation has a weak solution with initial condition y if there is a probability space with a filtration ft and a pair of objects y and L alpha such that L alpha is a stable noise without negative jumps, and y and L alpha together satisfy the weak formulation of the equation that I just displayed in the last slide. Okay, so next is the notion of weak uniqueness, and I say the solution, the solutions to the equation is unique in law or weakly unique if given two pairs y1 L1 and y2 L2 of solutions, and they can be defined on different probability spaces. They are both solutions in the sense that weak existence was defined. So L1, L2 are stable martingale measures without negative jumps, and Y1, L1 satisfy the weak form, and so do Y2 and L2 together satisfy the weak form. Y1, Y2 have the same initial condition, and then they must have the same finite dimensional distribution. So this is what is called weak uniqueness. This holds for every two pairs Y1, L1 and Y2, L2 of solutions. So contrast this with the more stringent condition of pathwise uniqueness, where Y1 and Y2, firstly, they have to be defined, if they are defined on the same probability space, then Y1 and Y2 are required to be equal in both their parameters with probability 1. So this is a much stronger condition, and we're not going to use it here. We are only interested in weak uniqueness. All right. So how are we supposed to establish weak uniqueness of the solutions to the SPDE? So the common way of doing it for stochastic equation is to transform it to a martingale problem, and to do that, I have to introduce a few notations. So MF is the set of all non-negative finite measures on the real line. D is all MF. D is a set of all Cadillac MF valued paths, and D has the Sparrow topology on it. And for and YT are the coordinate maps on D. Okay, so we have this. We have this martingale problem. So we say a probability measure P is on probability measure P on D is a solution to the local martingale problem corresponding to 1 if for every psi is a smooth rapidly decreasing function on R, this my object is a local martingale with respect to the filtration of Y. So my looks a little bit unintuitive, and I'm not going to be able to give a full intuition, but suffice it to say the first this delta term comes from the Laplacian term of the heat equation that we first described, and the second term, this ys minus to the power alpha beta comma psi to the power alpha, comes from the noise term. Okay, so in 2002, Leonid Mitnick proved that if I have alpha and beta such that alpha is between 1 and 2, alpha times beta is also between 1 and 2, and beta is between 0 and 1, then this martingale problem has a solution, at least one solution. I should mention that Mitnick's result is a little bit more general because he considered consider space dimensions, all space dimensions. We are only restricting ourselves to space dimension 1. All right, so our result is that under the same regime of alpha and beta, when the initial condition is smooth and non-negative, the local martingale problem 4 has the local martingale problem that we defined has a unique solution. So what are the difficulties? So there are a number of difficulties. First is that the solutions are not continuous in time, and the coefficients of the noise is not Lipschitz. These are the two main problems. And one way of addressing these is to, okay, so there is a moment estimate and I'll skip that. So one way of addressing these issues and to prove a general weak uniqueness of a solution to the martingale problem, we have to resort to a tool called duality. And duality comes from the following idea. So if we are working with martingale problems, then it is enough to show their solutions are solutions are unique. It is enough to prove that for one-dimensional distributions. So that will imply equality of finite dimensional distributions, which is what we want. So what does duality look like? So to establish the duality of y, duality with y, we have to find a suitable process z such that an equation like equation 6 here holds for all t, right? So y0 and z0 are, of course, the initial conditions of y and z respectively. And so I can have other functions other than the exponential, but exponential is a separating class on the space of distributions, and that's why exponential is what is desired. Okay, so to show this, we also have a bunch of integrability conditions, and once we prove the integrability condition and we show a relation like 6 holds, we have established duality, and the point of duality is that the existence of the process z will imply the uniqueness of one-dimensional distributions of y. That's the whole point. Okay, so in our case, we have a candidate process z, and the candidate is quite appealing, and the candidate process z follows the same form of SPD that we started working with, except two crucial differences. One is that the exponent of the noise, exponent of the coefficient of the noise changes from beta to 1 over beta, and the noise itself has index alpha times beta as opposed to alpha in the original stochastic heat equation, but the noise is of the same kind. It's a stable martingale measure without negative jumps, and we can formally check that if z satisfies this SPD equation 7, then the duality relation holds. But there are, as I mentioned, some integrability conditions are necessary, and they cannot be, they do not hold in this situation. So we have to find some other way of doing it. So one way of doing it is, again, an invention of the arithmetic, and it's called approximating duality. So it says that if we cannot have z in that relation, maybe we can approximate z by a bunch of a sequence of processes Zn, such that the duality relation holds, but only holds approximately for each n. So epsilon n is an error term, and we have to show using some moment estimate and so on, which we skip, that epsilon n goes to 0 as n goes to infinity, and this is enough to prove the uniqueness of one-dimensional distribution of the solutions to y. And so this is what we actually prove. Given y naught and z naught, if they are both non-negative smooth rapidly decreasing functions, there is a sequence of processes Zn such that Zn starts from Z0 for all n, and such that for all positive t, or maybe I think this is a typo. T should be in a bounded interval 0, big T. The duality, the approximating duality relation holds for each solution y which are independent of the Zn. And so this is the last slide that I wanted to share. And so these are some references, and thank you very much.
Thank you, Sayantan. Are there any questions? All right, so if there are none, then maybe we can accumulate all these questions and then ask the speakers for the first half of the session in the 15-minute break. So
I should stop the sharing?
Yeah, please do. Thank you.
Okay.
So maybe we'll move to Sarath. Thank you, Sarath. All right, so we'll move to the third talk. After this talk, there will be a 15-minute break. So now we have Sarath Yasodharan from ECISE, and he'll be talking about a sufficient condition for the quasipotential to be the rate function of the invariant measure of countable state mean field interacting particle system. So Sarath.
Thank you for this opportunity, and this is joint work with my PhD supervisor, Professor Rajesh Sundaresan. So I will begin with the system model. The model is that of a countable state mean field interacting particle system. So here, let Z denote the set of non-negative integers, and we consider n particles. Each particle has a state associated with it that comes from the set Z, and the state of the n particle at time t is denoted by xn of t, and it comes from Z. Now, these states change over time in a Markovian fashion, and there are certain allowed transition rates which are described using a directed graph on Z, and we denote that by Z, E. To define the transition rates, we have to first define the empirical measure of the system of particles. So the empirical measure is at time t is an element of the space of probability measures on Z, and the ith component of that will tell us what fraction of particles are present in state I at time t. So here the space of probability measures is denoted by M1 of Z, and we equip that with the total variation metric. Now, for every edge in the allowed transition graph, we are given a function lambda Z, Z prime on the space of probability measures, and we say that at time t, a particle in state Z makes a Z to Z prime transition at a rate lambda Z prime of the current empirical measure. So in other words, the transition rates of one particle depends on the states of the other particles through this empirical measure. Hence, this is called a mean field model. So this defines a Markov process. So here mu n is a Markov process. It's a countable state Markov process, and the state space of that is the space of probability measures on Z. And under suitable assumptions on the transition graph and the transition rates lambdas, this Markov process will be positive recurrent, and there is a unique invariant probability measure Pn. And in this talk, we are interested in studying large deviations for this family of invariant measures of this Markov process. Okay, before I describe the main results, I will quickly indicate the definition of a large deviation principle. So here the setting is there is a complete and separable metric space, and there is a sequence of S-valued random variables. So roughly speaking, large deviations theory helps us estimate probabilities of rare events. So it will give us estimates of this form. So probability that xn is in A grows like e to the minus n times a constant. So this constant here is given by minimization of a certain functional I over the set A. So more precisely, we say that the sequence xn of s-valued random variables satisfy the large deviation principle, LDP for short, with a rate function I if three things happen. One is that the rate function must have compact level sets. Then there is a lower bound. So this is called the large deviation lower bound. So for every open set, we must have this lower bound. And there is an upper bound for every closed set. And sometimes instead of this random variable here, we also write the law of xn instead of xn. Okay, so the goal is, recall that the goal is to study large deviations of the family of invariant measures. So in this setting, if we want to study large deviations of the invariant measure of a Markov process, first we have to, typically what we do is we first look at the process over finite time horizons. So here, first we can obtain a mean field limit, which is a typical behavior of this empirical measure process. So here, this so what we can show is that for large values of n, that is the number of particles, with very high probability, the empirical measure process mu n will be in a small neighborhood of a certain dynamical system, which is called the McKean-Vlasov equation. So we can also establish process level large deviations. So when we view this empirical measure process mu n as a trajectory valued random variable, we can establish that this family satisfies the large deviation principle with a certain rate function. So this rate function is a function on the space of trajectories. And throughout the talk, we will assume that this McKean-Vlasov equation has a unique global attractor, which we denote by psi star. Now, to study the large deviations for the invariant measure, we define this quantity called the Friedlin-Menzel quasipotential. So for this, what we do is we consider all trajectories that start at psi star, which is the global attractor of the McKean-Vlasov equation, and that reaches a point psi. And we evaluate the cost of this trajectory, that is the large deviation, finite duration large deviation principles rate function evaluated on that trajectory. And then we do the minimization, consider all paths that starts from psi star, end at psi, take the minimum cost among all such paths. So this is the quasipotential. And this quasipotential is actually the rate function for the family of invariant measures in many contexts. So for example, in the context of a finite state mean field model, this gives the rate function for the family of invariant measures. And similarly, for a model of small noise diffusions, this is a rate function. So in this work, what we first show that we first provide a counterexample where this quasipotential is not the rate function. So this counterexample is that of a system of non-interacting particle system. So here we consider n independently evolving MM1 queues. So each particle is executing an MM1 queue. That is, the transition rate is shown here. So there is a certain forward rate lambda f and a backward rate lambda b, and lambda f is smaller than lambda b. So in particular, the transition rates of one particle do not depend on the states of the others. So the particles are evolving independently. And since they are positive recurrent, there is a stationary distribution, which we denote by psi star. So psi star is a distribution, is a probability distribution on non-negative integers. Now, since these particles are evolving independently, an application of Sanow's theorem immediately tells us that this family of invariant measures satisfies the large deviation principle with rate function, the relative entropy. So the function is in the first argument, and the second argument of the relative entropy is fixed at psi star. Now we can approach the same problem through trajectories. So what we do is, so we recall the Friedlin-Menzel quasipotential, which is defined in terms of the large deviations rate function for the process, the empirical measure process. But here in this example, we show that this quasipotential is not the same as the relative entropy. So specifically, we show that there are certain points in the space, that is points in the space of probability measures, where the relative entropy is finite, but the quasipotential is infinite. So these points are precisely those points whose first moment is finite, but but this theta moment is infinite, where theta is this function z log z. So for all these points, the quasipotential will be infinite, but the relative entropy is finite. And as a consequence, since the rate function is unique, standard results from large deviations theory tells us that this quasipotential cannot govern the LDP for the family of invariant measures. So this is the counterexample. Now we propose some sufficient conditions under which we can assert that this quasipotential is indeed the correct rate function. So here are the assumptions. So first, we assume a specific transition graph. So the transition graph is shown here. Every node has two outgoing arrows, one to the immediate right and one all the way back to the origin. So this is our transition graph. We also need a condition on the transition rates. So we require this decay. So when we look at the forward transition rate from the node set to node set plus 1, it should decay as 1 by z plus 1. Okay, and the backward transition rates, they have a uniform lower and upper bound. We also want certain Lipschitz continuity property of the transition rates, and this Lipschitz continuity property is required to obtain the finite duration large deviation principle. And as I mentioned, there is a unique globally asymptotically stable equilibrium psi star. So under these assumptions, we can first show that there is a unique invariant probability measure Pn for this empirical measure process mu(n). And the main result is that under the above assumptions, this family of invariant measures satisfies the large deviation principle with rate function, the Friedel-Menzel quasipotential. So the main difficulty in proving this result compared to the finite state mean field model is that the space of probability measures on non-negative integers is infinite dimensional, and it is not locally compact. And since the quasipotential being a rate function has compact level sets, it cannot be continuous in that topology. And so certain methodology that people have used in the finite state space case do not apply here directly. So the basic idea in the proof is to transfer this process level large deviation principle for the empirical measure process to the stationary regime. And this was first done by Sovers for a model of stochastic PDE. So here, these are the main ingredients in the proof. So first, we prove a continuity property of the quasipotential. So the continuity property says that if psi n converges to psi in the space of probability measures, and in addition, if the theta moments converge, then we have convergence of the corresponding quasipotential. So that is the first property that we need to transfer this process level LDP to the stationary regime. So the second property is a process level large deviation principle for this family of empirical measure processes. So here we need slightly more than that. So we actually need a uniform LDP, where this uniformity is over the initial condition of this empirical measure process lying in compact subsets of the space of probability measures. And of course, we also need the strong Markov property of mu(n), and we also need this exponential tightness estimate. So here it says that the probability, so here we take the set of all points whose theta moment is less than some m. So under Pn, the probability of the complement of the set must decay exponentially fast. So these are the four main properties used in the proof. Okay, so to summarize, we studied the large deviations of the invariant measure in countable state mean field models. First, we provided a counterexample where the Friedel-Menzel quasipotential is not the rate function, and we then proved that under some sufficient conditions, the rate function is actually the Friedel-Menzel quasipotential. So here are some future directions. One is a uniform large deviation principle, where uniformity is over open subsets of the space of probability measures for the countable state mean field model. Now, once we have this uniform LDP over open subsets, then we can actually show the LDP for the invariant measure when the limiting McKean-Vlasov equation has multiple stable equilibria. Another future direction is to define a generalized quasipotential, where this generalized quasipotential will coincide with the usual Friedel-Menzel quasipotential under our assumptions, and it also governs the large deviation principle in our counterexample. So these are two future directions, and thank you.
Thank you, Sarath. So now we are at the end of these three talks. Maybe we can start with some questions for Sarath.